Okay, so as I said, you've only got a few choices for the way that the atoms can bond, and you also only have a few choices in the way the molecules can be arranged. So there's three types of reactions. These are your choices, right? And we have already mentioned these, but we're just kind of reinforcing this idea. So synthesis is one type, and that of course means that you're making something larger and more complicated. And you see this when we're putting together these carbohydrate monosaccharide units to form a disaccharide. So you take smaller, less complex reactants and you get a more complex product. So synthesis will be used for growth, of course, because you're adding, mass and matter, therefore, and storing energy, because when we put things together, that takes effort, and so there's potential energy stored in this bond. And we'd also need to do synthesis when we're repairing after damage. Decomposition basically is taking something more, larger and more complicated and making it simpler. So this is a process in which we release energy, right? So you can see these are opposites, if you will, polar opposites, right? And so decomposition or degradation reactions release energy and they supply matter, right? They supply these building blocks. And a classic example for this is digestion. Many reactions are reversible, so we could have actually drawn this as one reaction and just had an arrow pointing this way as well to represent both these reactions together. The last type of reaction is called exchange, and this is generally done for buffering purposes. So we don't talk about it as much. We're usually, again, I said a lot of what we deal with is centered around energy transfers. So synthesis and decomposition accomplish that. And then matter is supplied or bound up depending on what your need is. But exchange is when we don't really form a difference in complexity, and energy is not really the goal here. So I'll give you an example again. Buffers do this. Hydrochloric acid, sodium hydroxide, both very strong acids, strong base. When they get together, we just rearrange this and we can get a salt and water. And I say this is done for buffering acids and bases, which leads us to, how we do these reactions, okay? So, and what influences these reactions. So, and we're going to get to that. Acids and bases are going to have some influence on this, and we're going to do this in lab as well. So, factors which influence the rate of a chemical reaction. Well, we already talked about this idea of catalysts doing this, but it turns out that then, while the catalysts, which are normally enzymes, and that's what we're going to talk about, and they increase the rate of reaction, but they themselves are not part of the reaction. Enzymes, and therefore the reaction rate of the chemical reaction, how fast we can get this degradation, how fast we can get the synthesis, are affected by several physical things. So a classic temperature, right? So temperature dictates molecular movement, and the faster a molecule moves, the more likely it's going to get together and therefore have this this rearrangement and change in energy state. And so in warmer temperatures, molecules move faster. In colder temperatures, they slow down, right? This is one of the fundamental reasons why your body temperature is 37 degrees Celsius, because that's the optimum temperature for your chemical reactions to occur. It keeps those molecules moving fast enough to get the reactions, right? Because rates how fast, reactions working fast enough. Concentration and pressure effect. So again, if you have more of the molecules of the reactants around, that's, again, opportunity for the reaction to happen faster, all right? Pressure is going to allow, it's going to force them together. So I said if you add more molecules or limit the space they interact in, such as increasing pressure, forcing them closer together, there's more opportunity for contact, and therefore you get the rate of the reaction goes up, okay? So, and this is just tracking this progress to show the difference of what an enzyme can make. So when there is no enzyme, it takes more effort to get a reactant to change to the product. When enzymes are around, they lower the activation energy. And that reaction to product happens faster. Okay, so inorganic compounds essential to life and to human life, right? So oxygen, molecule, right? 2 oxygen atoms bound by a double covalent bond. We looked at this in the previous one. Turns out it's 21% of the atmosphere, and it's essential to human life. And this is one of our requirements from Chapter 1. Why? Well, because oxygen is used in cellular respiration, the process, right? A very important metabolic process which transfers energy from your food to ATP. All right? Carbon dioxide is an inorganic compound. All right? Okay, so this is actually not a compound, right? If we went back and we looked at that definition, but it's okay. We'll cheat a little. Carbon dioxide it has two different elements in it, and these are also double bonds, so both of these are examples of nonpolar covalent bonding to get them together. Okay, carbon dioxide is a very small percentage of the atmosphere and is actually toxic to the cells. When it is around, it will recombine with water and you get acids, right? Carbonic acid, which leads to hydrochloric acid. Where is carbon dioxide produced? Well, it's actually produced everywhere in the body because in the process of metabolism, cell respiration, we use oxygen, and so it's a reactant, and we produce carbon dioxide. And you have to have energy all the time, so you're always using oxygen, hence why you breathe, inhale, and you're always producing carbon dioxide, why you exhale, right? Inorganic salts, all right, so and these are generally compounds, and the salts are usually ionically bonded, just to reinforce those concepts. They are abundant in your body fluids as electrolytes. So because they are ionic bonds, when they are put into water that has polar covalent bonds, the charge on the water will pull apart the ionic bonds. All right, they play very important roles in your metabolic processes overall, in your clotting, like calcium does that. Magnesium is here. Neuromuscular function would be sodium, potassiums, calciums. And so I say, overall, you have to have a certain amount of these inorganic salts in your body in order to do all these different processes. And then again, water is an inorganic, right, compound, H2O. And we have to recall that the bonds that hold these atoms together, right, the two hydrogens and the one oxygen, are polar covalent bonds, as I mentioned, with the salts. So water is an amazing molecule. It's very good at maintaining temperature, so it can absorb a lot of heat energy. Okay, and so blood and sweat, which are mostly water, right, are able to pick up heat in the body and transfer it, and without changing their own temperatures. The blood's temperature doesn't change, the sweat doesn't change, but they can change the internal temperature by removing that heat. Water protects. It is part of those serous fluids that we talked about there. So it cushions around structures. It lubricates, right? So you're going to see it in synovial fluids as well. It is a universal solvent, as I mentioned. It's polar covalent bonds with the negative and positive charge in the same molecule are very good at interacting with other polar or charged molecules. So I say here that all reacting molecules, and we'll call those solutes, must dissolve in water to form solutions, because your body is based on water. It is the solvent in the body. If we're going to move things around in the body, those chemicals, right, reacting molecules, must dissolve in water. And we call those solutions. So your blood is a solution, right, your sweat is a solution, your cerebrospinal fluid is a solution, okay, there's solutions inside the cells everywhere, right? And then water is very good at transporting. As you've ever looked at a river or brook, right? It doesn't matter. And so blood being mostly water and lymph being mostly water are very good at moving things around in the body. All right? So the role for water in a chemical reaction, all right? So I say here that water is really key to two of the chemical reactions, the dehydration and the hydrolysis. So here I'm giving you some new terms for the same reactions, okay? So dehydration I've added to synthesis, and now the dehydration recognizes this role of water. So when two smaller chemical units, we just call those monomers, get together, right, water is removed, dehydration, right, and then so this is a dehydration synthesis. Simpler reactions form a more complicated product, water removed, all right. In hydrolysis, which is your decomposition or degradation, now we add hydro for water and lysis for breakdown, right? So now we have a larger, more complicated molecule. We're adding water to this reaction, and we're breaking it apart. And here you see that water is here, and the water is now incorporated here. And these are extremely reversible and important, right? So we could have gone either way. And they're often catalyzed by enzymes to control the rates. And they're extremely important to your life. All right? In ionic bonding, we get acids, bases, and salts. So as we've been talking about the inorganic stuff of life, acids, bases, and salts are generally inorganic, because organic means you have carbons and hydrogens. Right? So the types of electrolytes are your salts, and that's the general catch-all term, and then acids or bases are actually technically a type of salt. So another name for an electrolyte is an ion, right? So here's our sodium chloride, and here it's ionized, right? It's now pulled apart because the sodium chloride isn't charged, but once they come apart, they've got their charges. And you notice that they come apart because water dissolved it, right? And you know this, if you put salt crystals in water, the salt disappears, right? So why does that happen? Well, as long as there's more water molecules and we have this really negative charge associated with the oxygen, it will surround the positive, right, sodiums and pull them away from the negative chlorides. And you'll notice here, the chloride, right, is then attracted more to these positive, right, parts of the water molecules. And again, the key is that the water molecules are, that's why that's hydrated, are outnumbering the sodium chlorides, right? You know, if you keep pouring salt into a glass of water, you'll eventually get a saturation point, and the salt won't dissolve because there's a key number, right, or ratio of these molecules, right? I said, so you were collectively a bunch of solutions. I said about 42 liters of these. All of these use water as a solvent, and water is polar, right? So this is the rule. This is what happens in the body all the time. So electrolytes are the dissociation of these compounds. So in other words, what am I saying? You're never going to see salt in your body, right? Once it's taken into the body, it will be surrounded by water, and it will be an ion or an electrolyte. So the electrolytes are a result of this dissolving or dissociation of these, right, crystals of salts, right? And so we're also going to talk about specialized salts, acids, and bases, right? So acids and bases represented here on this simple cartoon, right? Here's, right, the water is, again, is hydrating or surrounding the acid, let's say hydrochloric acid, and it's pulling apart, right? The hydrogens are positively charged, the chlorides are negative, the water, right, is pulling these ions apart, and with the free hydrogen ions, we now call this an acid. If we decrease the amount of free hydrogen, we become more basic. And you can decrease the amount of free hydrogen by having these hydroxyls, because you notice they have a negative charge, right? So this is the concept that there's a balance, yes, one more time, between hydrogens and hydroxyls. So what is that balance? Well, think about it. What is water? It's H2O. So it is these hydrogens and these hydroxyls. So water becomes neutral because these are balanced. There's the same amount of hydrogen ions as there are hydroxyl. But in a solution that is more acidic or more basic, there's no balance. The balance is not there between the hydrogen and the hydroxyl. So here, if you release more hydrogen into solution, you are ultimately an acid, and your pH is less than 7. If you release more hydroxyls into the solution, you are a base, and your pH is greater than 7. And that's because a base can also accept hydrogens. The strength just depends on how well that compound falls apart in water.